Hello, everyone. It's such a pleasure to be here and to present some of the activities of the Indiana Center for Vascular Biology and Medicine. And the title of this talk is Changing the Course of Vascular Diseases. And this research was strongly supported with the help of the CMMRF. So it's actually your fundraising activity which make it work to contribute to find new tools to treat diseases for which in the moment is little cure or no cure at all. So the fundraising sparks this research to look into the mechanism, how disease works, to enhance the regenerative power of our body and to bring people back to life. And it's a teamwork, and it's quite international. So I, for example, am born and raised in Germany. I'm now American, but you see in this example that we are really as open society in that we are welcoming everyone who wants to join in this ambitious endeavor to induce regenerative powers to cure diseases. So I would like to point out one person who is the center's director, Dr. Keith March. Below, you find his team, Dimitri Traktuev to Pat Xell. They all contribute on this research, but they are not alone. Around them, here in this blue color, you have people being associated, like me. So I'm just one example. There's Eddie Schauer, Murph Yoda, Yang Chengdu, other researchers which use similar but slightly different aspect of repairing diseases and using the regenerative power for this purpose. So to give you a little bit an overview, what I will talk today is, I will tell you a success story of one stem cell type, the so-called adipose stem cells, which are kind of cell to rule the world because they can repair and be beneficial for so many diseases, including arterial diseases, diabetes, pancreas, stroke, and more, that they have really an outstanding function. They can also ameliorate COPD and other lung diseases. I will then go into my own research, and that will be entitled How to Stop Proteins When Breaking Bad. And I will also allude a little bit in one of my research topics, which is to analyze why stem cells age. So we think they are immortal, right? But some of these stem cells we are using in therapies are actually not. And some of our stem cells in our body, they are not immune against inflammation, for instance. And then I will bring some overview about how this research can benefit patients as soon as possible. What are adult adipose stem cells? And here I'm bringing data which were pioneered by the work in the laboratory of Dr. Keith March. So stem cells like AAC cells are single cells which have the unlimited potential to replicate themselves. They have also the ability to secrete factors. And these secreted factors are mostly beneficial for the body. And we are just in the process of understanding this. So they protect, they repair, and they regenerate. And to start with the research here, and to find ways how to improve their repair, protection, and regeneration potential, that's our ultimate goal. So where can they be found? These adipose stromal cells were first found surrounding the small blood vessels. So blood vessels are the highway of our system, supplying the whole body with blood and nutrients. And these cells can be considered as repair stations along these highways. These AAC cells We are the first FDA-approved study for patients to receive own fat-derived stem cells. And I go a little bit into some of these examples. So I will pick out actually a particular patient. So we're talking about a patient who was able to walk less than 20 feet due to leg pain. He rolled into the hospital with a wheelchair. He reported it was awakening each night with pain 8 to 10 times. He had to use opiates. And his expectation was to do things with the family in the future and not being wheelchair bound and homebound. So here's the procedure room. On the left side, you can see the team of surgeons trying to get ready for the aspiration of the stem cells from fat tissue, from adipose fat tissue. Then you see the middle, the aspirated material in little syringes. And then it goes into something, a machine. You see here this blue-coated lady standing in front of this, what Dr. March always calls the cappuccino machine, where these stem cells are separated from other body components. And then, success. The cells are purified, good yielded, and here in this bedroom picture, you give these stem cells back to the patient. And the family is awaiting, and the next day, things are looking already better. And the patient was able to walk half a mile twice daily, do Christmas shopping, would sleep much better, had less pain, and was able to do a family trip to Florida. So this is a single case of success story. There are much more telling us the ultimate power of these cells. And that's where this team efforts come in. Another team member, Dr. Shekhar Gangaracho, who, like myself, wasn't born and raised here. He's originally from India, but he's American now as well. He wanted to know how stem cells can be of benefit for diabetic retinopathy. So he started something what we call the ICBM eye research activity. And in animal models reflecting diabetic changes, you can induce something like diabetes in rats or in mice as well. He could show that the impaired vision with diabetic mice could be almost completely normalized with treatment of this adipose stroma stem cells. So that was published. Another group could show that another ICBM group could show that stroke, in the ischemic stroke model, stem cell application could secrete factors leading to protect the brain from injury. So in this analyze pictures from brains, you see that on the right panel, the brain looks pretty much like the healthy, non-challenged brain to the very left. And the middle brain shows all this edema and swelling and damage of the neurons, which would, if it was a people, not a rodent, would reflect massive impairment through the stroke reaction. So the ICBM has also wound burn healing research. They are trying to use either extract or release conditioned medium from this stem cells or the stem cells themselves to help the skin to grow and to repair. There's another group, ICBM group, which is focused on pancreatitis research. Here again, I will not go into the details, But you just see in the middle panel how bad a pancreatitis model can damage your pancreas and how human adipose stromal cells can benefit and kind of reverse it to a normal looking tissue. Then I will lead to something what is also part of my own research. It will be the efforts ICBBM have been undertaken to treat and hopefully find a cure for emphysema/COPD. That disease affects 3.1 million in the United States alone. There's no cure. There's only palliative treatment. You can improve the actually breathing problems to some extent, but not in a long-term way. In the end, you are left with oxygen treatment and exacerbation. It is a disease with a downhill course. It is a disease of small blood vessels again, and you can treat it. There's actually new research that even when small rodents, which had acquired emphysema through prolonged exposure to cigarette smoke, receive these stem cells, they can reverse the disease. So we have the ability not only to stop the progression of the disease, but also to repair them. And that is also part of my research, and I will show you a little bit later some of our attempts to increase repair activities. So the understanding of emphysema nowadays is that there are endothelial cells and blood vessels which are actually dying. And on the upper panels you see a picture. It is a mouse scanning EM picture, which is kind of reflective of what you will see in a patient with computed tomography. And you see many little black holes. These are the lung air sacs, which can expand and fill with air. In the lower panel, you see a diseased lung, and you have overstretched air sacs, which are now not able to recoil. There's much less surface area to be able to transport the oxygen to the blood vessels. So the blood vessels here would appear as white matter, in the air would appear as dark matter. So vascular damage and vascular loss, endothelial cell loss, is a key factor which we are addressing. And we found out that when we test these mice in smoking models, yes, we let them smoke. They like smoking. They become addicted like normal living beings as well. Yes, with giving human AC cells to these mice, we can block disease progression. And these data are not shown. These are very new data from the laboratory of Dr. March. They can also reverse disease. Similar effects we got with a monoclonal antibody, which we have humanized now, so we can give it to patients in hopefully soon in clinical trials. This antibody captures a protein which is normally not outside of the cells. But when cells are stressed by cigarette smoke exposure, for instance, this factor is called EMAP2, is released, and it becomes a toxic factor. And to stop this toxicity, which is part of feed-forward loops leading to the progression of the disease, can actually block the progression of disease development, shown here in terms of airspace normalization and lung function normalization with this antibody. So there's a huge challenge. There are still roadblocks or water blocks ahead of us. And one is that we know that there is something which is beyond our control right now, which is a genetic disposition. So there's also only alpha-1 antitrypsin. Sorry, this is autocorrection mistake. It should be trypsin, not tyrosine. This is a deficiency which is only found in circa 3% of the population. And that can only explain to a certain extent why some people are more prone for cigarette smoking to develop emphysema and maybe also associated with that lung cancer than others. So what is the genetic disposition? That's our research to this, in order to improve the antibody treatment we can offer soon, and in order to improve the adipose stromal stem cell treatment. So the ACs, alpha-1, antitrypsin, and neutralizing antibodies can stop inflammation in cells induced by cigarette smoke. And that's what we know now in preclinical studies, and we are going to bring this into clinical studies with your help as well, hopefully, as soon as possible. So what else could be important to do research on? And one of the questions I already mentioned is, can stem cells age? And we found, yes, it can. Cigarette smoke and inflammatory factors, they cause this aging. We'll bring some data soon. And we think if we can find out what causes this premature aging, we can return the cells to become practically immortal and to do the repair function. Because one of the problems is with people who are smoking for decades, that most of the stem cells are gone. There's a nest, as we say, and we don't have them able for treatment. So that is something what we want to target. We know that there are stem cells which reside in small blood vessels, which are giving rise to endothelial cells. And in comparison to bone marrow stem cells, we call these cells endothelial colony-forming cells. So we have a hierarchy of stem cells which can expand rapidly to form mature endothelium. Normally, they have a low aging range, which we call low levels of senescence, but that changes, as shown here in this picture, when we treat these cells with bacterial toxins or with inflammatory factors, or not shown with viruses. So you may remember viruses like CMV being discussed for cardiovascular disease risk. So that's promising research we have. I'm not going to show you too many details, but results we have identified a molecular mechanism to protect the cells from premature aging. So now in the future, we, the Indiana Center for Vascular Biology and Medicine, are part of key new programs starting 2015, going to 2018, partially 2019. And we are very hopeful that also with your help, we can start a couple of clinical trials. So here I would just like to mention the CCTRN network. These are clinical trials in legs and soon heart. There's another first trial to treat legs with one own fat-derived stem cells, and I think I have shown you already one example. Then we want to start trials with COPD, pancreatitis, diabetes, and COPD, emphysema. So with that, I would like to conclude, thank all these funders we got in the recent years to make all these exciting research activities possible. And I would like to particularly thank the Cryptic Masons, all the donations which were really helpful for all of us. They gave to the Medical Research Foundation. Then, of course, the CE CCTRN, the NIH, the IUPI Signature Centers, and the VA Center for Regenerative Medicine. So with that, I thank you for your attention. I hope you enjoyed this very quick overview about activities of the Indiana Center for Vascular Biology Medicine, and I hope that you got an idea what is our potential to employ regenerative medicine to treat diseases. Thank you.